Hello. With a lot of pleasure, I am happy to introduce Nidhi Singhai, who is a senior security software engineer at Red Piranha, and Vagisha Gupta, who is a security software engineer at Red Piranha. There's a fun fact. Vagisha was an outreach intern with OISF where she worked with SuriCata Update and was immediately hired by Red Piranha, which happens to be our consortium member. So here's to Nidhi and Vagisha.
Thank you, Shivani, for an amazing introduction. So, hi everyone, I am Vagisha. Hope you all had a great lunch and you're ready to brace up for our amazing talk. So, we are from Red Piranha, and in today's talk, we'll be talking about detecting lateral movements with SuriCata multi-tenant setups in zero trust network architectures. So, who are we? This is an amazing caricature from Frank, who just happened to notice us yesterday, taking all the insights from the amazing talks that we were listening. So, I'm Vagisha Gupta. I work as a security software engineer at Red Piranha. It's been 3 years that Red Piranha has hired me. So I am mostly working with rule management, threat hunt dashboards, network mapping, database restructuring, and VPNs with Red Piranha. In 2019, I started my journey with InfoSec and mostly in development through OISF. So I participated in this amazing program, which is Outreachy. And I happened to start my open source journey with OISF. And at the end of the internship, Red Piranha, which happens to be the consortium members of OISF, hired me. So I'll be handing over to Nidhi, my colleague Nidhi. She'll be introducing herself and we'll be beginning our talk. Thank you.
Hello, everyone. I'm Nidhi, and I'm a senior security software engineer with Red Piranha. I have around 16 years of industry experience spanning across telecom, networking, aerospace, and I've been with Red Piranha for more than 4 years now. My core work includes networking, routing, high availability, IDS IPS engines, secure web gateways, and proxy servers. I was involved in the 60 Gbps IDPS throughput that we tested for Crystalli XDR with the help of Peter. So what will we be covering in this talk? We'll be talking about multi-tenancy in zero trust network architectures. We'll be talking about multi-tenancy options that SuriCata provides, how Crystalli is implementing multi-tenancy. Then we'll be using SuriCata to detect lateral movements within an enterprise with a few lab examples. So what is zero trust network architecture? We have all heard a lot about it. So what is it? Basically, trust no one. And what it does is it creates a logical access boundary across an application or a set of applications with policies that govern access and control. Now, why do we need ZTNA? It's mostly because of the change in which our working environment has advanced. So with BYOD, remote work, VPNs, also our network perimeters have expanded. So we have moved to cloud or hybrid cloud deployments. And it is also a natural extension of principle of least privilege to network architecture, and it reduces the likelihood and impact of cyber attacks. What is multi-tenancy in a ZTNA? So what it does is it creates different network segments or perimeters based on traffic patterns. It creates different security profiles depending upon the criticality of data and access controls. Also, multi-tenancy is a system-wide concept. So it provides system-wide control access across different applications for different traffic. So SuriCata has a built-in multi-tenancy support as well. So what it does is we have multiple rule sets that can be used and variables that can be used in SuriCata, a different YAML config for each tenant with root variables and files. So it supports multiple networks. So we can have a mapping either which is based on VLANs or devices. So different tenants have different mappings. Also, it has the amazing Unix socket support. So it provides an ease of configuration for registering and unregistering the tenant. So this is a sample config that SuriCata provides. We enable multi-detect there. We choose a selector which can either be a VLAN or direct devices. So we identify the tenants and we identify the config that should be used for each tenant. We map our VLAN or devices against individual tenants, and off we go. Now, what were the limitations that we were facing in Crystalli for this? So multi-tenancy in SuriCata is supported at the detection layer. So like Peter was talking today about, I don't want alerts sometimes. I just want to act in a tap mode. And I want to just receive the traffic. So I cannot use multi-tenancy there. Then, as of now, IPS mode is not supported. So the supported capture methods are PCAP, fpacket, pfring, and netmap. In Crystalli, because of our perimeter expansion and networks, we wanted granular mappings, which would be based on devices and groups, users. So groups can be anything. And we also wanted different loggers for our analysis. So how did we approach multi-tenancy in Crystalli? So just like SuriCata, we have 4 pillars. The first is multi-network, where we identify different networks that would be using different tenants in SuriCata. Then we identified multi-run modes, depending upon the network access. So sometimes I need a span mode, or I need a detection mode, or an IPS mode. Everything can run in the same device. Then we have different rule sets for different segments. This is the same as SuriCata provides. So we can tune different rules, and we can use them in the different segments. And then we bring it all together with multiple loggers and use it in our threat hunt dashboards. Now, what is the network aspect of multi-tenancy here? Now, in a single device, as I mentioned, we might want to use a span port for a different traffic where I'm in parallel to another device. Or I want to be a bit more lenient with the user data for the net access. So I want to use an IDS mode there. Or I might need stricter policies for access to my servers. So I might need inline policies. And everything can run in the same device. So for span mode, we have the NSM mode. For user data, we can use IDS mode. And for critical traffic, we can use IPS mode all in the same device. Now, what are the different run modes? I'll quickly go through this. NSM, as we know, it disables detection. So we don't load any rule set. So no alerts would be there. We are just capturing the data. In IDS mode, it is an AF packet mode. And we identify the interfaces that we want to run SuriCata on. And that is defined at the command line. And interface config has different cluster IDs. That is a very important thing, that the cluster IDs have to be unique. In case of IPS mode, our run mode is AutoFP, and we use firewall rules to direct the traffic to the different SuriCata queues that are corresponding to different instances. So what are the rule sets? So we take the publicly available rule sets, and we have our own Crystalli sensors as well that due to incident response and SIEM, we collect all these rule sets in our common SOC. These rules are curated, and they are divided, and different archives are generated, and they are divided into different groups, like balanced, connectivity, custom. So what this does is you are differentiating your rules so that you can use them in different tenants. And they help improve the security posture. For different loggers, you have individual logger for each tenant. You can do selective logging, so you can enable or disable logs based on the traffic that you expect to see on that segment. Also, this gives ease of access and filter for threat hunt dashboards. So how does it all fit together? We have implemented multiple tenants using multiple profiles. Now, what is a profile? It is a simple instance of SuriCata. So we have a separate YAML config for each instance. We run a separate Unix socket for giving Unix commands. Then we have a separate fpacket config for the different interfaces that we'll be running this instance on. And we have separate queues when we want to run in the IPS mode. So how do we start the profile? We give Suricata, and we have a different PID file for each instance, and the location of the profile config. So the profile config, it includes one default file as a fallback option. Then we have a separate network config and address variable for that particular instance. So we don't use the default variables. We use the variables that are specific to that instance. Then we have a separate Eve logger for different logging instances. We'll talk about how we do that. Then we have separate app parsers about which parsers we want to enable on that particular tenant. Then a separate rules.yaml for the rule set that we choose for a particular instance. fpacket config, as we mentioned, and an fq config, and a separate Unix socket. So as I said, we wanted IPS mode in multi-tenancy as well. So how have we implemented IPS? So we have different queues for different profiles. Right now, we support single queue, but we'll be, as suggested by Eric, we'll be looking into multi-queue soon. Then we have different marks for different profiles. So we use IP tables for marking our packets, and it happens in the Mangle table for identification of the flow. But we use a common NFQ repeat mark. So yeah, so we start Suricata as we did for fpacket mode. We just choose the run mode as AutoFP, and we identify the queue which is dynamically created for that profile. As I said, our repeat mode, we specify the same repeat mark and mask there. Now, why did we do that? Because we did not want to complicate, and we did not want to use a lot of rules in IP tables, as you can see ahead. Now, how do we do the IP table rule handling? In the Mangle table, we identify the source and destination for which we should be using this profile. So your source and destination can be an IP address, it can be an interface, it can be a user, it can be a client device, anything. So we can even use IP sets here. So IP tables gives a lot of options there. And we identify the profile where it should be going, and we set a particular mark for that profile. So if you have two different IPS instances running, you'll have two different marks for those two IPS instances. Now, in the filter table, we first forward that, the first inspection that happens, and we forward it to a separate different chain that we have created as IDPS. So the first check in the IDPS is whether any mark is set or not. So it can either be a profile mark, or it can be the NFQ repeat mark that we have configured. If nothing is set, then this packet is not supposed to go to any of the Suricata instances. Now, next, we check if the packet repeat mark is set. If it is set, so then we don't again need to go beyond. And after that, we check which particular profile this instance should go to, and we forward it using an FQ to that particular profile's queue. Now, how do we use multiple rule sets? We use Suricata update for our multiple rule sets. We give the URL from which we want to download, which is our server. Then we give the rule set specific update config and the output directory. And our rule management happens, so we modify each individual rule set. We can modify, update, add. So everything is individual rule set specific, and we use Suricata update for that. We even have local rules options. So there can be certain profiles where you're creating rules on the spot specific to an application. So the local rules option can take care of that. So what are the multiple loggers that we use in multi-tenancy here? So we have an instance-specific Unix socket for Eve logs in suricata.yaml. So as you can see, the Eve log config has file type as Unix stream. Now, what we do is our IDPS logger, it continuously listens on this stream, and it enhances the data as well. So as I was saying, that you might need certain controls based on end user devices or usernames as well. So this data enrichment can happen in the Eve logger, and all that is inserted into MongoDB. So a lot of times what we are worried always about is the performance considerations when we are running a lot of instances of Suricata. So a few things that we need to keep in mind about performance here is network segmentation is very important. We cannot be running all the instances on all the interfaces and on all the data. So that would definitely add on to the CPU cycles. So, and different networks that share the same characteristics can share the instances and profiles as well. Also, we should ideally use a single network segment in a single profile. About the rule sets, networks that share rule sets, again, share characteristics, should ideally be included in the same profile. And rule sets tuning is very important here. So how does this all fit into zero trust network that we started with? Now, data from different loggers can be fed into the AI/ML engine. So as I said, you can dynamically generate your rule sets as well. So you can create baselines based on your end user devices, time of access, and you can use data sets to identify and list those devices. So any anomalous behavior from those data sets can be stopped at the perimeters with strict IPS profiles. This also helps manage access control across internal networks, which helps us in detecting lateral movements. Now, Vagisha will talk about how we are using Suricata to detect lateral movements in our networks.
So I'll be giving some snapshots here to see how we are using Suricata and analyzing the metadata that Eve provides us to detect lateral movement in our systems. So what is lateral movement? I'm sure you have all heard the amazing presentation that Peter gave us. He gave us some insights what lateral movement is. So lateral movement is a process in which a threat actor enters a remote desktop by downloading a malicious program from the desktop, and with the help of that entry point, it enters the various devices in the network and moves laterally across the network until it has reached his final target. So how Crystalline and Suricata comes into picture in the lateral movement. So once the threat actor enters the network devices, with the help of Suricata, our system detects and prevents the lateral movements that are happening in the network. So I'll be giving an example for the RDP-based lateral movement. According to the Mitre attack, it has been classified as T1021. So it all starts with a malicious program. What RDP is, remote desktop is a feature which allows users to log into the desktop with the help through GUI with the help of a remote setup. So attackers connect to the remote system over RDP. So connection is established by downloading a malicious program. It uses brute force credentials to perform authentication. It performs the action on the target, moves laterally in the system network devices until it has reached its final target. And after what it aims to have achieved, after it has achieved that, it disconnects from the network devices. So this is an example that I'll be showcasing from our snapshots. We'll be doing some analysis from the PCAP, public PCAP that we have fetched. So the attacker's IP that we have noted is 194.61.24.102. There will be RDP access to domain controller, which has an IP of 10.42.85.10. There will be a lateral movement connection to a client desktop having IP 10.42.85.115. And after the malicious program has been downloaded, you will see that the host machines will access the command and control servers, which has an IP of 203.78.103.109. So the PCAP that we have picked up is the analysis has been done by dfirmadness.com. The PCAP name is K001, which is publicly available, and you can use that PCAP to perform your analysis under using Eve or any other platform that you want to. We are using our internal system to see how threat hunting for lateral movement is done. So in the snapshot here, you can see this is the UI, how our UI looks like. So we have applied the filter source IP and destination IPs, and we can see these two IPs that I already told you about in my previous slides, one ending with 10 and one ending with 115. These are the IPs on the local network. Looking further into these IPs, if you want to check the host names for these IPs, we have applied filters, a DNS filter resource record name, and we can see the record name that it has fetched is Citadel DC, which appears to be a domain controller. And for the IP that is ending with 115, it has given us the name as desktop SDN. So if we want to see what is the incoming network from internet to this local network, we have added both the IPs as destination IPs in our filters, and we can see that there are around 29,000 requests from this external IP that is 194.61.24.102, and the destination port appears to be 3389, which is the remote desktop connection. So we get an idea that something suspicious is happening here. So the remote desktop connections from internet to the domain controller is occurring. For this external source, if we apply this filter, and we have, as you can see in the snapshot, that we have applied the external source IP as the filter, and we can see that Suricata has given us the top events, TLS, file info, and alert. Okay, so we get an alert. We'll see what that alert is about. If we investigate that alert event, we can see the source IP, the external source IP. We can see the source port is the remote desktop source. The destination IP is that of the domain controller. The rule that has been captured, the signature that has been captured, is RP-scan RDP connection attempt from Nmap, and the category of the rule is detection of network scan. So when we feed the Eve data to our MongoDB or to our databases, we do some data enrichment. In that data enrichment, we also input the GeoIP details based on the IP addresses. So for this source IP, the GeoIP details that we get is the location is Moscow, Russia. So this alert has been detected with this following GeoIP detail. If we want to investigate a little more to see what was happening right after the alert was generated, we can see that, please check this in the descending order. You can see right after the alert was logged, there were multiple RDP connections attempts made from the external source to the internal host. So now that we know that something is suspicious with this external source, if we want to check what was the incoming traffic from internal host to this external host, we applied the filters. We kept the source IP as our internal host and the destination IP as the external source. And we can see that there were 2 HTTP requests that were made. If we look deeper into these HTTP requests, so we did some aggregators, and we saw filtered out the aggregators as hostname, URL, content type, and HTTP methods. We can see that that the local host machines did a HTTP GET request to this external server, and the file that was downloaded was coreupdater.exe and another one from the root directory. So it appears to be a MS-DOS program. If we look into this GET request, we can see the source IP as the internal host. The HTTP hostname is the suspicious external source that we are investigating. The HTTP UR is the malicious, suspicious file that was downloaded. The HTTP method is get method, and the protocol is HTTP 1.1, and the size of the file is 7168 bytes. So with the help of Wireshark, I was able to fetch this file into my system, and I did a hash lookup for this file. And then with the help of VirusTotal, I saw what other users reported for this file, and 59 out of 71 users reported this as a malicious program. So now that we know that, okay, 194.61.24.102 appears to be infected source, we applied the destination IP as that to see what is happening, which all IPs are retrieving that file. We can see both our domain controller and the internal host, the one ending with 10 and the one ending with 115, appears to download that file, coreupdater.exe. Okay, so when we investigated a little more further into what was happening just right before and after the file was downloaded, we can see that Suricata logged anomaly event for both the internal hosts. So as you can see in the snapshot that the client is trying to connect to 203.78.103.109 over port 443 after downloading the exe file, which means that once after that file was downloaded from the external source, both the internal hosts did some requests to the control and command servers. So if we look deeper into what anomaly event recorded, so we can see that anomaly type was app layer. The event that was recorded was app layer protocol detection skipped, and the anomaly layer was proto-detect. So application layer proto-detection script occurs when when the Suricata is not able to get much information about the protocol, either the traffic is undetected or, that's why it recorded an anomaly event. So what happened right before the app layer protocol detection script was recorded? We can see that the alert that I already mentioned, it was just a few minutes before the anomaly for this external source starting with 203 was recorded. So if we see at the flow of events based on the timestamp, starting from the bottom, you can see at 2:19 there was an alert from the source IP was 194.61.24.102, and the destination IP was the local IP. So that means that RDP connection was made was made by this external source. Right after that, you can see there were 3 HTTP requests for the domain controller that is ending with 10 IP. Right after that, you can see there were 2 anomaly records. So that means after the RDP connection was made, the file coreupdater.exe was downloaded. And right after that, the requests for the domain controller was sent to command and control server. The same thing is we can see for the client host that is ending with 115 IP. So we can see the coreupdater.exe file was downloaded through HTTP request, and the anomaly was recorded. So looking at this pattern, on the next slide, if we make some more filtration, we can see that right after the anomaly was detected, so if you can see here, right after the domain controller anomaly was detected, we can see that there is a destination port of 3389, and the source and the destination IP, the source IP is the domain controller and the destination IP is the internal host. So there was an attempt to RDP connection between the local hosts. That means right after the file was executed, there was an RDP connection made inside the network. That means there was a lateral movement in the internal network. And after the RDP connection was established, you can see for the other IP, that was the internal host ending with 115, there was a HTTP request made to the external source, and the file updater was again downloaded to other local network. So this is how we saw the lateral movement between these IPs, and how we use Suricata to detect lateral movement in our systems. Now coming to how do we correlate between Suricata and other applications in our system. So we are using the flow ID in Suricata to correlate between different events in our system. And to perform the correlation across other applications like web proxy, Netify, firewall, we are doing a match based on source address, source port, destination port, HTTP metadata fields. So we do a match, we generate a hash ID based on these fields, and based on that, we do the match across the different applications in our system. So this is how we are detecting lateral movement and performing multi-tenancy in our setup with the help of Suricata. Thank you. Any questions? Oh, Jeff has a question.
Well, that was great. Thank you. Did you consider using the built-in multi-tenancy support within Suricata at all?
Yes, so as I mentioned, we wanted IPS support, which was a prime requirement for us. That's why we thought about using different queues and running Suricata as separate instances. Because Suricata, as of now, we know that it does not support IPS. So, yeah, that would be a request.
Are you using dataset? No, too bad. That was yesterday. Are you using IP set or a technology like that in NetFilter to do the mapping between the group parameter and the tenant?
So we do use IP sets. So we are using IP set in different forms, but so yes, all the groups that we create, it's always IP set so that they get updated in the back end. We don't have to reload the IP table rules. So yeah, it is IP set.
No other questions? All right, you got off easily. Their first SuriCon talk, hopefully we will see you guys back again. Thank you so much for being here.